Okay, we're looking at linear functions like in the real world. So how would I use this to describe a situation? So here's a situation I have for you. Leslie has been the winner of the annual tricycle race for 2 years in a row. Other students want to defeat her. Who will beat Leslie in the big race this year? Okay, so Ben is going to ride at a constant rate of 1 meter per second and starts at the starting line. So we're going to fill out his table right now. And I know that since we are measuring how far they are going, that's going to be the y variable. So the y is equal to the distance traveled in meters. And so in meters per second. So we compare where they are depending on what the time is. So it's the time in seconds. All right, so write the equation. Okay, so we're gonna do the table first. So if Ben starts at the starting line, then the distance he's traveled so far is 0 meters. That's the starting line. And it's also been 0 seconds. The start of the race is 0 seconds. And then it says he travels 1 meter per second. So if I add 1 meter, how many seconds do we add? We add 1. Basically, that's his 1 meter per 1 second. Okay, so we're going to add 1, giving us 2. We're adding 1 to 1, giving us 2. And then at 3 seconds, he's at 3 meters. So we're going to write the equation of his race in slope-intercept and slope point form. So in slope-intercept, well, I better find a slope. It looks like he travels, if I compare, actually, I'm going to find the slope. Y1 minus y2 minus y1 over x1 minus x. Oh, I said that wrong. X2 minus x1. So this, I'm going to take away this is my x2, y2, and my x1, y1. So I'm going to subtract 1 minus 0, 1 minus 0. And then I need to subtract the difference in time. So 1 minus 0 again over 1 minus 0. So 1 minus 0 is 1 over 1. So he travels 1 meter per 1 second. Hey, isn't that what I said over here? 1 meter per 1 second. That's how fast he's moving. Okay, so then I need to find his y-intercept. So when the time is 0, his distance is also 0. So the b value is going to be 0. So I get the b is equal to 0. So in slope-intercept, mx plus b, I get y is equal to 1x plus 0, or y is equal to x. This is my slope-intercept form. I'll give you more room on your paper. Okay, so then for slope point form, the slope doesn't change. We're still going 1 over 1, okay? And then you choose a point from the table. Let's choose this point. So this is going to be my x1, y1 for slope point is 3, 3. So slope point is y minus y1 is equal to the slope times x minus x1. I get y minus 3 for my y1 is equal to 1 times x minus 3. And this is one possibility for your slope point. Okay, so let's go ahead and look at the next writer. Okay, so JT has a constant rate of 2 meters per 3 seconds and gets a 5-meter head start. So let's start with his head start. So at 0 seconds, JT is already at the 5-meter mark. Okay. And then it says every 2 meters, every 3 seconds, he changes 2 meters. So for every 2 meters, he changes 3 seconds. For every 3 seconds, he changes by 2 meters. So after 3 seconds, where is he going to be? Well, he's going to gain 2 meters from where he was. So 5 plus 2 is 7, okay? 7 plus, we're going to gain another 3 seconds, which is 6. He's going to gain 2 more meters, which is 9. If he gains 3 more meters, 3 more seconds, it's at 9 seconds. And 2 more meters, so he'll be at 11 meters, okay? So we're going to write the equation in slope-intercept form. My b is equal to 5, and the slope is equal to the change in y over the change in x. So the change in y is 2, and the change in x is 3. Or we can see the rate is 2 over 3 seconds. Okay, so 2 over 3. So this the equation in slope-intercept form is y is equal to mx plus b. So I get y is equal to 2/3 x plus 5. Okay, so the slope tells me how fast he's moving, and the b value tells me where he started from. Okay, in slope point, we're going to choose a point. It doesn't matter which combination of which ordered pair you use. I'm going to use this second to last one. Okay, so the point is going to be 6, 9, and the y and the slope is still the same. So we're still changing by the same rate, which is 2 over 3, x1, y1. So slope point says y minus y1 is equal to m times x minus x1. Okay, so we're going to substitute it in. So y minus 9 from the point is equal to 2/3 times x minus, I look at the x value from my point, which is 6. So y minus the x value, which is 6. Okay, so then slope, this is slope point, and slope intercept is how we wrote it in the beginning. Wow, that was not legible. Okay, all right, so we're going to use the equations to find where each rider will be at 22, the rider will be at 22 meters, and then where will the rider be after 8 seconds? Oops, you know what? We're going to do, so where will the rider be? When will the rider be at 22 minutes, and where will the rider be at 8 seconds? Okay, so if we're talking about 22 meters, if I'm thinking about my ordered pair, my x and my y, remember x represented the time and y represented the distance in meters. So I'm going to take a look at JT and Ben. Ben's equation is y is equal to 1x, or y is equal to x, and JT's is 2/3 x plus 5. Okay, am I going to substitute the 22 in for the x or the y? Remember, 22 represents the y because it's 22 meters. So, and we're going to figure out what is the coordinating x value, or the coordinating time, that would give me a distance of 22 meters. So instead of the y, we're going to replace the y with 22 in each of these equations. And then Ben's is easy because we don't have to solve for anything. So it says that when x is equal to 22 seconds, Ben is at 22 meters. Okay, so when the time is 22 seconds, Ben is at 22 meters. All right, so we got to do some work for JT. We're going to subtract 5 because that is the inverse of adding. Okay, so I get 2 over 3x is equal to 17. Then we're going, since 2/3 is multiplied by x, I can multiply by the reciprocal to undo that operation. Okay. Or divide by 2/3, that's also an option. So I get 1x is equal to 3 times 17 is 51, I believe. Yeah, 51. Okay. I get 51 over 2, which is equal to 25.5. And we're talking about x, so that is seconds. So if I were to say this, when the time is equal to 25.5 seconds, JT is at 22 meters in his race. Okay, so who gets to 22 meters faster? Well, looks like Ben does, right? Takes him less time to get to the same distance. Okay, moving on to this one. So where will the rider be after 8 seconds? So again, we have Ben's equation is y is equal to x, and JT's equation is y is equal to 2/3 x plus 5. This time, when I look at my coordinating x's and y's, y is seconds, y is distance in meters, okay? So we're talking about 8 seconds, so that would be my x value, 8. So now we're looking for the coordinating y value. So instead of x, I'm going to replace x with 8. So in this case, we say when the time is 8 seconds, Ben is at 8 meters. Okay. All right, let's do JT's. JT's y value at 8 seconds would be 2/3 times 8 plus 5. So 2 times 8 is 16 over 3 plus 5. Get a common denominator, so times 3. So I get y is equal to 16 over 3 plus 15 over 3, which is 31 over 3, which is 10.3 bar. So when the time is 10.3 bar seconds, no, when the time is 8 seconds, sorry, because that's what we substituted in, 8 seconds, JT is at 10.3 bar meters. Okay, we're going to pause because my Apple Pencil's going to die. Maybe we will pause. Okay, next we need to graph the equations for Ben and JT's races. So you can use the table to graph, but I'm going to use their equation. So for Ben, wow, my hair. The equation is y is equal to x. So I can see that the slope, there's an invisible 1 and an invisible plus 0. So the slope is 1 and the y-intercept is 0. Okay. For JT, which I'm going to do in blue, his equation was y is equal to 2/3 x plus 5. So the y-intercept is 5 and the slope is 2/3. Okay, so we need to clearly label in our axes. I'll do it in green. So I'm gonna make this line my y-axis, this my x, so I can see a lot of the axes that's in the first quadrant. Okay, so I'm going to count by ones, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 18. And I need to say that this x-axis is equal to the time in seconds. And then the y-axis is equal to the distance in meters. Okay. So again, I'm going to count up by 1, 2, always counting from the origin. The origin is 0, and then I count up from there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 17, 18. Okay, so for JT, he starts at y is equal to 5. So I'm going to start at 1, 2, 3, 4, 5. And then for every 3 seconds, he gains 2 meters. So I'm going to go up 2 over 1, 2, 3 seconds. Up 2 over 1, 2, 3. Up 2 over 1, 2, 3. Back into my robot counting. Okay, I'm going to go ahead and connect those. We don't have negative time, so I'm going to go ahead and just start my graph at x is equal to 0. Okay, for Ben, who I'm going to graph in purple, the y-intercept is 0 because he does not have a head start, and his slope is 1. So we're going to go up 1 to the right one, up 1 to the right one. For every meter, he gains a second. For every meter, he gains a second. For every meter, a second, so on and so forth. So I see we get all of these points right here. Whoa, I can't believe that turned into a line for me. Okay. It's not very good though. Doesn't quite want to go where I want it to go. Let's try this again. One more time. I'll just draw it in. It's not going to be straight, but that's okay. Okay, so we need to answer a few questions now. Okay, so the purple is Ben, and the blue is JT. Okay? So according to the graph, who won the race? Well, it depends. Okay, so for number 1, who won? Well, Ben wins if the race lasts more than 15 seconds. And then JT wins if the race is, his line is above Ben's between 0 seconds and 14 seconds. So actually for Ben, he wins if the time is more than 14 seconds, excuse me. Okay, so JT wins if the race is between 0 Actually, we'll just say 0 to 14 seconds. And then they tie if the race is exactly 14 seconds. So actually this one, we should write it in interval notation. So 0 is less than x is less than 14 seconds. Okay. Okay. So this means that if the race lasts for anything above 0 seconds, but less than 14 seconds. Okay, so 13.99999 seconds, and JT still wins because his line is above Ben's. Okay, their lines meet at 14 seconds, and then after that, Ben is ahead, or he's traveled more distance because the line is above. Okay, for number 2, how far is Ben after 16 seconds? How can you tell from a graph versus an equation? So Ben is the purple line. So I would go to 16 on the x-axis and go up to where the graph intersects. I would go up until I intersect the line. So I would see that at x is equal to 16, y is also equal to 16. So Ben is at 16 meters when x is equal to 16 seconds. Okay, in the equation, he has y is equal to x as his equation. So when the time is 16, so when y is equal to, when I replace x with 16, I get y is equal to also 16. So he is at a distance of 16 meters. So to find the coordinating x or y value in an equation, you just substitute it into the equation. If you're looking for the coordinating x or y value on a graph, you just look for the ordered pair on a graph. Okay. Number 3, 2 more. So when in the race is JT at 8 meters, how can you tell on a graph versus the equation? Okay, so first we're going to look at JT at 8 meters, and I'm like, oh, 8 meters. That is the y value. Meters is y. So I have to go to 8 on the y-axis right here. Okay, and then I make a line over to JT's graph, and it looks like right here, the time, I'm thinking that the time is about 4.5 seconds. So for number 3, from the graph, I'm going to look at the ordered pair, something comma 8, and that something is, I think, 4.5 comma 8. In the equation, I'm going to substitute in 8 for y. So y is equal to 2/3 x plus 5. That's JT's equation. And for the y, I'm going to substitute in 8. So 8 is equal to 2/3 x plus 5. Then we solve to find the coordinating x value. So undo the plus 5 by subtracting. I get 3 is equal to 2/3 x. Multiply by 3/2 to undo the multiplication. 3/2. So I get 1x is equal to 9 over 2. 3 times 3 is 9. 2 times 1 is 2. So that's 4.5. Oh, isn't that the time that matches where I saw it on the graph? The point on the graph? Yay! Okay. All right, last one. We're going to solve algebraically for JT's head start. So that means, and then how is it represented on the graph? So JT's head start on the graph is represented by his y-intercept at 5. So you can see that at time 0, he has a y value of 5. So to solve algebraically for JT's head start, what we need to do is, like, we're asking us, where is JT at x equals 0, at time 0? Head start is at 0 seconds. Like what's happening at the beginning of the race, right? So we're going to solve for y is equal to 2/3 x plus 5. And the 0 is going to become the x. So y times 2/3 times 0 plus 5. 2/3 times 0 is 0. So I get y is equal to 5 meters. And there we go. We can see our head start, that we can basically see that with at 0 seconds, JT is already at 5 meters. That's where he started from. Okay, so don't forget to do your analysis or your summary for this